Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about a new topic. So before I get into it, I really want to kind of build this up a little bit more, just so you have some intuition for what we're going to be playing with for the next little while. So we're going to be talking first about Turing machines in this lecture. Now, just to give you some background on Turing machines, these were initially proposed in the late 30s by Alan Turing. You may know that name. He's often affiliated or claims the title of one of the fathers of modern computer science. At least he's definitely one of the fathers, if not often regarded as the father of theoretical computer science. Depending on how people would like to talk about it, he's most certainly one of them. A lot of the foundational theory that he worked on in this time period would most certainly be applicable for what we're going to talk about in the next little while. So in the time period, he proposed a computer-like model of any possible computation. So in Turing's work, I believe he called these things automatic machines or A-machines, but we're going to call them Turing machines, named after, obviously, the person that introduced these types of models. So just as another aspect of this is you're going to notice that I'm going to be trying to kind of motivate that the model that we're going to be working with is essentially going to be what we're going to think about as computation, which is going to be very weird if you've never seen what a Turing machine looks like, because it isn't really like something that you would imagine on your laptop or something like that. But believe it or not, this Turing machine model is actually capable, or at least matches, a general purpose computer. So just giving you a heads up. So we're often going to be studying Turing machines to better understand what we're capable of solving from a problem standpoint, or in particular, if we want to think about it as languages, what languages we can recognize, at least with a computational machine. So hopefully this gives you an idea where we're going with this. So you're going to mainly see me trying to use this machine to understand things from the limits of computation. So it sounds very deep because it is a very deep subject. So I'm going to be trying to wade us through this topic very carefully, because there's a lot of different things I could be talking to you about, ranging from computable functions, and I'm sure there's maybe some people in the class I'm aware of that are familiar with some of that theory. I'm not going to be talking so much about that aspect of this, so-called recursion theory. Some people may be familiar with this. I'm going to be focusing primarily more on this Turing machine side and how it relates to the framework we've been presenting and building up this entire time. So just to give you an idea of how we're going to define the Turing machine, it's going to consist of three parts. So the first one is that it has a finite control. So you could think of this just like when we had our DFA, we had a set of states and we transitioned from one state to another state. So you can think of this finite control having this ability, at least when we're talking about the Turing machine at this stage. The next thing it has is a tape. Now, this is where it's going to get a little strange, because so far we're okay with this idea. We had this idea before when we were talking about the push-down automaton, right? This is where it gets a little bit weird. We're going to have an infinite tape. It extends infinitely to the left and infinitely to the right. And on here, all of these little squares, well, technically they're rectangles the way I drew them, but we're going to say they're squares just for the simplicity of things. These are called cells, and the tape consists of cells. So these cells are initially marked with what we call a blank or blank symbol. So that's what these B's here represent. So these are so-called blank symbols or blanks. So at the beginning, what's going to happen is each one of these cells is going to have some symbol in them. And when we start using the Turing machine, what happens is the machine gets loaded with input, and this is going to be your input string. And these are input symbols, and each symbol gets placed on a cell of the tape, where there's this third part of the machine. This is the tape head. The tape head, at the beginning of the execution of this Turing machine, will be pointing at the first symbol that is a part of the input. So we have this tape head. This tape head will move left and right along this tape. So just to be clear, a tape head, so this is that little arrow there, that is the tape head, when at a cell, allows the Turing machine to scan a cell. So it begins at the leftmost cell of the input. But here's the thing that's going to be a little bit unique to compare to what we've been doing up to this point. So when we're at one of these cells, the finite control, of course, will scan the cell. So it'll read it, but it also has the ability to write. So it can read and write. So that's a very important thing you should be aware of, is that we have the ability to read the input, but also write to this tape. So that means that the input isn't necessarily read-only anymore. Now it's actually, you can modify the input. So we have to be very careful when we talk about this Turing machine. So does everybody understand the main idea? So we have the finite control. It's going to be very similar to how we had it, so it moves from state to state. We're going to have this tape, and this tape has a bunch of symbols on it. They start off all as blanks, but when the machine is going to get started, it gets loaded with the input. And we're going to have this tape head, which can read and write to cells on the tape. It initially starts at where the first symbol of the input is on the machine. So are we okay with this setup so far? I want to talk next about how we perform moves on this Turing machine. Okay, I think we're good. Let me proceed then. So we're going to talk next about moves. So I'm giving you more of an informal introduction to this so that we can really start drilling down a little further. Now, one thing I want you to notice about this is it's going to be a little bit different, because up to this point, we've been taking advantage of non-determinism very often to talk about things that usually have more computational capability. Just as an example, when we talked about context-free grammars, and we also had the PDAs, remember we had like epsilon moves, for example. You're going to notice very quickly that these things are actually not anything to do with this. It's going to just simply be, I read a symbol, I can move to another state, and then I can write tape symbols on the cell that I read. But let me get into those details when we get there. So a move of the Turing machine depends on two things: the state of the finite control, so the current state you're currently in, and of course the tape symbol that you read on this tape. So on this tape. So what happens is this head is at a current cell. It reads the cell, and depending on its state, it will change state, so meaning that it could go to a different state, or it may stay in the same one. It will write a tape symbol to that cell, which may be the same symbol as there was before. So for example, when I'm right here, it may be possible that this X1 gets changed to a different symbol. This will be among so-called tape symbols, or it could stay exactly the same. One remark I do want to make that you should be aware of is that all of the input symbols are tape symbols, just not the other way around though. So it changes state, it writes to that tape, and then it moves. So that head can move left or right. So the head gets moved left or right. Now, I'm going to assume that it only moves left or right. It can't just stay in the exact same state at all times. So it only has two options. When it reads that state, it reads the symbol on the tape. It could change state, it writes to the symbol, and then it moves. But it only can move left or right. It can't stay in the same spot. Now you might ask, Dan, does this restriction do anything to us when it comes to talk about the Turing machine? The answer is no, actually. It doesn't constrain the model at all. Because you can actually define the Turing machine in many different equivalent ways. One way is including having it where it doesn't move. It has it so it can either go left, right, or stay in the same spot. It doesn't, by restricting it like this, we actually don't lose anything. When I say don't lose anything, it still expresses the same set of languages that it would do otherwise. But I need to stress for you that there are several equivalent ways to formalize the Turing machine. So what I mean by that is that when I'm going to define this Turing machine to you, depending on who you talk to, they may have a more convenient definition that they may use, that they may like. But there's a couple standard definitions that people tend to use. I'm going to present one of those to you. But if you are familiar with other definitions of the Turing machine, you may say and look at my one and be like, I don't know, I learned this a different way. And that's okay, because it's like there's some simple way to prove that they're actually equivalent to each other. So I must stress that the way I'm going to define it for you, there could be other ways. I'm going to define it in the way that the Hopcroft book defines it. But if you look at the Sipser book, they actually define the Turing machine ever so slightly differently. For example, they may explicitly define something called an accept state and a reject state. And our Turing machine will not have such a thing. But it's very easy to make it so it has such a thing. So let's proceed. So just be aware of these two things, that it has these three parts. And when we have moves that occur, we may move to a different state. We write a symbol to that tape, and then we move left or right. So let's talk about what a Turing machine is. So some things I've talked about here we're going to allude to, and we're going to build on top of it. I'm always humbled by teaching this topic because it is a fundamental topic. I must stress, just to be very clear, like the Turing machine is actually one of the most fundamental computational models of all of theoretical computer science. So like you cannot escape, like when you talk about theoretical computer science, you cannot escape the Turing machine. It's a fundamental model in computation. And most theory is built off of these things. So just be aware of that fact. But there's a lot of other convenient models of computation that are equivalent to the Turing machine that may be convenient to use. Depending on how far we can get along in this class, I'll probably talk more about this. So let me talk about how we're going to define the Turing machine. So some of this is going to feel like I'm just showing you something that you've seen before. Other things is going to be new, just like when I did the PDAs. In fact, I'm going to hopefully convince you that the Turing machine is actually a little easier to understand than the PDA because of a couple facets of it. But let me define the Turing machine for you. So I'm often going to abbreviate Turing machine as TM. And for those that are Pokemon fans, I'm not talking about those types of TMs. So just be aware of that. So it's going to be a 7-tuple again. It's going to be a 7-tuple. A Turing machine is a 7-tuple, which has Q, sigma, gamma. So far, this will look really similar to you, but they're going to represent things maybe slightly differently. Delta, Q0, B, and F. Like I told you, these things, they start stacking on top of each other. Exactly. So here's the 7-tuple. So you might guess what Q is. Q is a finite set of states, just like what you would expect. With a finite set of states. And this is, of course, of the finite control. Just to be clear what I'm talking about. I'm talking about that box that I had in my picture. Sigma is a finite set of input symbols, just like what we had. Finite set of input symbols. So this is no different so far. So far, we're not doing anything any different. Now, gamma is not going to be a set of stack symbols. Instead, they're going to be tape symbols. Are the tape symbols. I must note for you, like I said earlier, that the set of input symbols is a subset of the tape symbols. I'm going to skip over delta for now, because I want to define that afterwards. I always do that. I don't do it to spook you. Don't worry. You're okay. This one actually isn't too bad. I would argue that, like I said, it's going to remind you a lot of what we did with the PDAs, but it's actually not that bad. Q0 is the start state. So we're going to have a start state just like we had before. So we have a start state. Of course, this is a part of the set of states, right? So it is one of the states. Then we're going to have B, which is going to be among the tape symbols, is the blank symbol. It's the blank symbol, or just some people like to just call it the blank. And I must note for you, note that B is not an input symbol. So just be aware of that fact. It's not an input symbol. And, as I said earlier, and they appear in all tape cells except those finite cells that occupy the input. That's not any different than what I said earlier, right? And then, of course, we have our final states. So F is the set of final or accepting states. It's not too bad, right? Like a lot of these things we've seen at some point before, just we have this tape business that's going on a little bit differently, right? This isn't too bad, everybody, right? Does everybody understand what we're talking about when we talk about all of these so far? Give me a thumbs up if we're all good. It's always, like I say, it's always humbling for me to teach this to you because this is a very important model of computation. Like I've sort of alluded to at the beginning of this lecture, like this model of computation, it has played a very fundamental role in the development of computer science. It's basically where a lot of this started. Not necessarily everything, but most certainly the modern aspects of what we call an algorithm and all that. This is where it all started. Like our formal notions of these things. So now I have to define delta for you. So the good news for you, it's still a triple. I don't have more things I'm going to throw into this thing. So delta is a transition function. And has the form. And I should be more precise. When I say triple, I mean the output. You're going to feel like I went a step back and made something actually a little bit nicer to work with. Has the form delta QX. It's only actually a pair for the input, where Q is a state and X is a tape symbol. Remember, that's what I said earlier, right? Moves depend on the state and the tape symbol that you read on the cell. So now this is how I have to define the output for you. So this is where it's going to get a little strange, is that I'm going to have the ability to not define a transition for you. So if I give you some state and a tape symbol, it's very real that I can not define actually the output for you. So you can think of it as being empty, but it has a very special function in a Turing machine. So if defined, so I must stress that we allow delta qx, delta of qx to not be defined. I'll get to that in a bit, of what that does to the machine. The output of delta qx is a triple. So this is the part I'm talking about with the triple. Is a triple, and this should match exactly what I said earlier. Is a triple pyd as follows. So remember, I told you that we are going to have it where it may go to a different state, may transition to another state. It may write to the tape another symbol, or may not change it. And it moves some direction, right? So that's what this triple is going to represent for us. So P is the next state in Q. So that's the first one. Y in gamma is written to the cell being read, replacing the symbol that was previously there. And of course, the third one is the direction. So D, it belongs to one of two possible representations, an L or an R is a direction. Either left or right. Left or right. The direction instructs M which direction the head moves. So just to reiterate, D is either L or R, meaning left or right. The direction instructs M which direction the head moves. So it's going to move either left or right. So just remember the picture I showed you earlier. You're going to have it where it's at the tape cell. It may change what that symbol is. It may, actually first, it may transition to another state. It may rewrite the cell, and then it moves left or right. So does everybody understand what our transition function looks like? Like, it really is actually kind of cute if you look at it like that way. It's actually very simple also. Like, this triple looks really, like, we've dealt with things that look like this before, but really all it is just I go to this state, I write this to the symbol, and then, sorry, to the cell, and then I move left or right. That's really it. Now, the question I have for you is, do you see epsilon anywhere in this? Is epsilon anywhere? Does anybody see an epsilon? So actually, believe it or not, that when I don't define it, that actually has a very special purpose with the Turing machine. There you won't encounter epsilon. But yeah, no, that's a really good guess. That's actually a very good guess, because I obviously haven't said anything about this definition. I'm going to tell you actually very shortly what happens here with this. But yeah, no, do you see where I've defined anything saying like, oh, y is equal to epsilon, do something. Notice that really there's nothing involving epsilon here. So is this machine deterministic or non-deterministic? Exactly, exactly. Yeah. Notice that I only go from one state to another. I don't have it where like it's all over the place, right? It's always, as the way we've defined it, it's really just I go from one state to another state. It's deterministic, indeed, which should be kind of surprising to you because a lot of the things that we've done in the past, where like we have the PDAs and everything, they often will have it where we have these non-deterministic elements to them, right? But this one does not have that. But I will assure you, some of these things start creeping in every once in a while, and it's going to feel a little unsettling. So just be aware of that fact. But yeah, so this machine is in fact deterministic. Later, I'll be showing you a non-deterministic version of the Turing machine, but not quite yet. So now I want to tell you about a few things about how this is going to work, because I haven't yet formally defined for you really how this Turing machine accepts. Because that's usually what I do, right? Like usually we do some fun example, and then I like tell you, oh yeah, no, notice it will accept this way. I want to give you some heads up, just some assumptions I'm going to be using, and they will be informed by our definition. But I just want to give you some assumptions about delta that you should be aware of. So these are remarks or assumptions involving delta. So just so the first thing I need to do is I need to tell you how those undefined transitions exactly, the so-called undefined moves. We're going to be adopting the PDA-like language, or I'm going to tell you that I'm going to move from one configuration of the machine to another configuration of the machine. How exactly, when I don't define the transition function, how exactly that works. So a Turing machine halts. That's going to be a very important key phrase, so please keep this in mind. Halts whenever delta of qx is invoked, but is not defined. So just to elaborate on what I mean by this, if the TM, Turing machine, enters a state queue scanning symbol X, there is no move. There is no move, so it cannot move any further. So the intuition that you may have about the PDA, remember I had moves and I try to get as far along as I possibly can by consuming symbols. We're going to take that kind of intuition, but remember, it's not going to be nearly as complicated how the execution process plays out. So it's just really just as soon as you find it where you're at a spot where you invoke that transition function, when it isn't defined, you just assume that there's no way you can move any further. That causes the machine to halt. So stop. So it stops the machine. So now I got to tell you a little bit about what happens how you know something accepts or rejects. But I'll define these things more formally in a bit. Well, particular acceptance, because that's the one we really care about at this stage. If the machine is not in a final state, when the machine halts, it rejects the input. So this is how we're going to define rejection in a Turing machine. So if it halts and it's not in a final state, we're going to say it rejects the input. How about when it goes to a blank? Believe it or not, that's okay. It's okay if it goes to a blank, believe it or not. We can actually define, you'll notice that the way I define the transition function you'll notice that I'm allowed to use any tape symbol. The blank is in fact a tape symbol. So yes, you can actually have it where you can go to the tape, you can read a blank, and then you can go left or right. You're going to find that sometimes that's actually kind of handy to do. Okay, so that's how we're going to define rejection. I usually find that when you get through this the first time, it's really like, okay, well, what does that mean? An easy way I describe this is my playful way of describing this to you, is that you could think of this like it actually is a computer. So think of it like it is like your laptop or something. And it does something that you don't intend it to do, as in it tries to do something, but you find it is actually defined for you. What does your computer do? Like, it probably crashes, right? So that's the way I like to think about this, is that if I'm not in an intended state, I'm in a non-final state, and I find no way I can make any more moves any forward, you can think of it like the machine crashes. Just like a computer crashes. That's the way I like to think about it. However, you're going to notice that for acceptance, so if the machine halts in a final state, then it accepts the input. Then it accepts the input. So if you find it run into the situation where it's like, oh yeah, I don't have that defined, and you're in a final state, it accepts. Now, I'm going to make an important assumption here. Now, I don't necessarily require this assumption, but it's going to be a very useful one for us, because you can always define a Turing machine equivalently without this assumption in place. But I am going to make this assumption. For our Turing machines, there will be no moves out of a final state. So that means, of course, if you were to like imagine, like you'll see in an example in a little bit, but you can imagine it for regardless of what the tape symbol is. If you always see that's undefined for a state, then surely it can't transition, it can't make any move, right? That's what I'm going to assume is going to happen for our final states. Final state. So the TM, or Turing machine, always halts when the machine is in a final state. So this is an assumption we're going to make. You'll see how I'm going to use this in a bit. So this is why I really like using the analogy that this is crashing the machine, because it's absolutely unintended to happen. It's something that you don't want to happen, but this allows you to safely halt the machine, is that it's in the accepting state. So there's also another possibility that can happen. Now, up to this point, we've always talked about accepting and rejecting of the input, right? Now, believe it or not, there is a way to have this happen also with PDAs, but I must stress that in a Turing machine, there is a third possibility that can happen for a given input. So I'm just going to say, be aware. The Turing machines are not guaranteed to halt. So you can think of like an infinite loop in a program. And that's typically how it will play out. So this is a third possibility. This is a third possibility. And just to be very clear, in this case, it neither accepts nor rejects. So just it's very important to know that if it doesn't halt, you can't say it accepts or rejects. It's just looping on forever. So just be aware of that fact. This sometimes is a good thing to think about. Other times it's kind of the bane of our existence. Yeah. So there is no such thing as a computing bound on this. So like it will literally, in the theoretical sense, it will literally run on forever. So, because this is, of course, an abstract machine, there is no finite cap on how long it can take. But there is actually some classes of Turing machines where we can guarantee that it is going to accept or reject. I'm going to give those a name depending on how much time we have here today. But the Turing machine more broadly, it's allowed to have this third possibility happen. So we have to always be careful when we're designing these Turing machines. Sometimes it has its benefits, other times it has its benefits, at least from a theoretical standpoint. It is another phenomenon of the Turing machine that makes it interesting. And this will hopefully creep more in as we proceed in this part of the course, is that this third part actually gives us a lot of things, but it also is like a poison. So let's do an example, just to lighten that up. I'm getting all dark here about talking about poisons and stuff. I mean it figuratively. I'm talking about it from a logic standpoint, that by getting this much power, we're getting some things that maybe or maybe not we might not be able to handle. But you would agree with me that having, like, we write programs all the time that have infinite loops in them, right? But usually when we design algorithms, we don't like it when they have infinite loops. So, like I said, I'm going to have a very natural way of talking about these things in either today or maybe even next time. So let's do an example, because I want to have fun with an example here. So let me just make sure I got... here we are. Wonderful. So let's do an example. We'll start with something kind of cute and small. So here's a Turing machine, M. I'm going to define it where it has two states, Q0, Q1. It's going to have input symbols A and B. So that means that the input's going to be comprised of A's and B's. The tape symbols, I'm just going to make A, B, and the blank. Then I'm going to have delta. And then I'm going to have Q0. That's going to be my start state. Then I'm going to have the blank, and then my only final state is going to be Q1. So I'm going to show you a cute example. This should hopefully give you a nice visualization of how this is going to play out. And I'm going to show you a couple different ways you could represent Turing machines. So I'm going to define delta for you, where delta of Q0 A is going to be equal to the following triple. It's going to be Q0, B, and R. Then I'm going to have delta Q0, B. So when I read I'm in a state Q0 and I read a B, I'm going to stay in Q0. I'm going to write to the cell a B, and I'm going to go right. And lastly, if I read the blank symbol when I'm in Q0, I'm going to move to Q1, the state Q1, where I'm going to write the blank, and I'm going to go left. So you might ask what this does. So I want to do an example, and then I want to ask you what you think it does. So let's consider when the input W, so this is the input string, is equal to BAA. So let me start up the process here. So just to make this a little easier to see, I'm going to start off with the blank symbol on the furthest left. So I'm going to BAA, and then I'm going to have my blank on the right. And this goes on forever. Oh. So anyways. Oh, so question for you. Where should the tape head begin? Where should it be? Should it be right here? There? Where should it be? Yeah, the lowercase b, perfect. So this is where Q0 is going to start here. Now to make this a little easier for me to see, I'm going to have a different marker to show you when I'm ever going to rewrite a symbol. So let's see, so far I'm in Q0, because remember that's the start state. So I'm at a B, so I read the B, so I'm scanning this B. I look in my transitions here. I see a B I have Q0. I read a B on the cell. It tells me to stay in Q0. It says, okay, just write a B there, and then you're going to go right. So notice it's already a B, so I'm not going to change anything. But keep in mind, it really doesn't make any difference from a theoretical standpoint. So then I move to the right, and I still stay in Q0. So far, is everybody okay with that first move? So I was in Q0, I read a B, so I went right. And I just left the B because I already had a B there. Remember, it doesn't really make much of a difference because if there was already a B, it writes a B, it doesn't change. So next, notice that I'm at this A with Q0. I read an A, so notice I have it right here. Q0, when I read on the cell an A, it tells me to stay in Q0, but write a B, then go right. So we're definitely not going to have this A here anymore. Well, that marker is very sad. That's a very sad marker right now. Can everybody see that B? Okay, I'll assume we're okay. Yeah, I see a check. Yeah, wonderful, wonderful. So that means now I go right. So I move the tape head to the right. And it's still in Q0. I see another A. I apply the same process again. I write that as a B. And then I go to the right, right? However, now look, I'm still in Q0. I encounter the blank symbol. That's this guy right here. I'm in Q0. I read on the tape cell a B. So it tells me I have to I have to move into Q1. I need to write on this blank symbol the blank symbol. And then I move left. But now notice, so the B doesn't, the capital B, that's our blank symbol, doesn't change. But I move left. I move left, but I'm in Q1. Do you see any valid moves for me to make once I'm in Q1? No, right? So this means that now the machine is going to halt. And because Q1 is the final state, we say that BAA, it accepts BAA. And then we're done. That's it. Believe it or not. It feels a lot simpler than the PDA. How do you feel about that? It feels more mechanistic. It feels more like I'm actually looking at some computing machine, like an actual, very tangible thing. It just looks really kind of strange because we normally don't think about oh yeah, there's these tape cells, I move left and right. But I feel like this is just my thoughts. I don't like to usually talk about my thoughts in lecture, but I feel like this feels like a step down in terms of complexity in describing things to you than the PDA. How do you feel about that? I think it's mostly the determinism that really kind of gives me that impression. But like I said, this is a rather general model, as strange and simplistic as it looks. But I'm going to get to that when we get there. But I have a question for you. Can somebody tell me what this Turing machine does? What does it do? Like, don't have to tell me a language, just tell me what it does. Yeah, starts at the left and moves all the way to the right, and wherever it sees an A, it replaces it with a B. And that's all it does, right? It just goes left to right, and wherever it sees an A, it replaces it with a B, right? And that's all it does. That's all it does. So this is the cute Turing machine that, and notice that regardless, you'll notice quite quickly that this will always halt, right? There's nothing weird about this machine. It always will go towards the right, and it will eventually encounter a blank symbol because the number of input symbols for W is finite. So I want to talk about a couple of things before we stop for today. So the first thing is I want to talk about how you represent Turing machines. So there's a couple of different ways you can do this. So I'm going to first give you one right about here. The first one is talking about a transition table. So naturally, I can have a transition table. It's actually quite a bit simpler than you would expect it to be. Keep in mind, like, all you have are your states. You're going to list your states here. So I have Q0 and Q1. And then I'm going to have my tape symbols, A, B, and blank. And then all I do is I put in my triples. So all the triples I have over there. So when I have Q0 and an A, I have Q0, B, and to the right. For B, I have, let's see over there, we got Q0, B, and to the right. And lastly, for the blank, this is the one we have Q1. And then I leave the blank as is, and I go left. So notice that what I'm going to say to you is, notice, just like my example over there, Q1 does not have any moves that are defined. So you'll notice that if I represent it as a table, the accepting states will always have it where the row just looks like this. So these dashes just mean I haven't defined it. Some people like to call them empty, but I'll just say that these aren't defined. So are we okay with this table? I want to draw you a transition diagram as well. And I assure you, they're also quite nice and simple to draw. Just the problem is when we want to start building things with these Turing machines, they can get quite complicated. So there's our transition table. Now, I must stress that you could add more information to this table, but this should be sufficient if I gave you that formal definition I have over on the right. You notice I'm not starring or drawing arrows anywhere on my table. This is typical when we're designing or describing TMs. Just usually when we do this, we define everything over there. We have our 7 tuple. So here's another way you could represent this. Here's the transition diagram. I'm going to adopt a lot of conventions of the pushdown automaton. So I'm going to have my start state. So I label start. These are typically nice because you can see everything except for the blank symbol. That's usually assumed just to be capital B. So this is the thing that's great about this is that you can just take everything that you've seen in this course up to this point and you can say, oh yeah, that makes sense. So here's our final state here. And for the transitions, I'm going to label them like this. So notice, remember I had my move that takes me, we're on a blank symbol, and then it takes me and moves me left. Well, so the way I'm going to define these things is that whenever you see the first symbol, that's what you read on the tape. This symbol is the one that you're going to use to rewrite over the tape with this. Nice and simple. And of course, the arrow I'm using tells you the direction. Note, I'm not going to be very picky about whether you actually draw an arrow or you say L or R. Usually, I use the arrows just because sometimes you may actually have it where there's literally an L and an R in the input, in our tape symbols. So that's why it's used a little differently. So I still have two transitions here well, two moves. I should be very careful about this, because I can transition from one state to another, but the machine itself goes from one configuration to another configuration. So remember, I have it where I can read it A or B. So remember, when I have an A, I rewrite that as a B on the tape, and then I go right. When I have a B, I make sure I write or keep the B there, and I go right. And believe it or not, this is our Turing machine description here as a transition diagram. So believe it or not, that's all I have to say today. So when I come back, I'm going to be formally defining what the language of a Turing machine is, and we'll talk about some other classes of languages. So when we come back, we'll look more into Turing machines. We'll see some more examples, okay? So that being said, I want to say thank you very much, and have yourself a beautiful day. I'll see you later.